let's go to the circuit, detection circuit here. The way that we have there, after pass the pinhole, you have a grating and you have an array of at least 32 APDs detectors, and also have 2 PMTs here. So you can take the whole spectrum at once. And we discovered that we had to order separated. You can have a wheel here with filters that can send your light to an output port. It did not come with the system. I believe it would come, but we had to buy it separated. So we can send this, and after you send this, you can just put a small 30 centimeters monochromator with some notch filter there and take the wrong spectrum. And the nice thing about this is that everything passes through the pinhole, so everything is confocal here. So you can have random spectrum. The idea is to stop at some point into your sample and take the random spectrum and see what you have there. It's not to make images out of this. To make images, you need another thing. And by looking at the 32 detectors, then you can combine them and make the images with different colors and see the spectrum. At these detectors, they have a bandwidth of 10 nanometers, so it's not that great in terms of the spectroscopy, but it's enough for fluorescence. And I want to talk about this one, as I think it's a quite important technique, that's fluorescence lifetime imaging here. And the idea is that we can, as soon as we send the electron to the excited level, it's going to come down. And because it does have charge, anything that interacts with the electron here will change the time of the decay. So it's very sensitive to change in the local pH, ion concentration, anything that has to do with charge or dipoles here. It is going to change the lifetime here, which is everything that happens inside the cells. And the idea of the instrument is that we can measure each photon, the time that its arrival time. It's actually, you have kind of a charge-discharge capacitor, and we start this with your fluorescence pulse, and as soon as the laser pulse comes, you then turn it off. And the voltage is proportional to the time, so you can make this and actually pass this through a monochromator and have 16 channels here. For that you have the lasers being scanned, see, here, but on the other part, you don't want the laser to be scanned on the entrance of your monochromator. So the other part is in the arrangement of the slit. So you can have all these 16 here. For each photon that arrive there, you can see the wavelength and the time of arrival of the photons. And with that, you can then construct nets that depend on this kind of lifetime decay here. And so the color is going to be dependent on the lifetime, and actually you can fit this with 1 or 2 exponential or 3 exponential and get lots of information out of this. And that's a technique that depends pretty much on the chemistry around the molecules that are fluorescent. If you wanted to extract second hormone generation, which is ultra fast, so it's coherent with the laser from fluorescence, you can use this time-gated SAG. It's everything is combined here, but I only see the second hormone generation because it's fast, and the fluorescence comes later. So, and the last equipment, it's already in Brazil. It's not installed there yet. So you see that I'm going to use this part here for the output tweezers. The laser comes from behind, and this upper part here, before the condenser, you can use to put a system that is AFM system for near field optical microscope. That does not make anything through your optical measurements here. So the thing that you do is that as soon as you take this tip very close to your sample, it can enhance your electromagnetic field for 10 to 6, 10 to 7. So you only see the signal very near to this tip here. That's a contact technique, so you can only see surface, but surface in biology is kind of a universe. Everything happens at the surface of the cells there. So you see, you can see the round spectrum here if you approach the tip, and then if you retract the tip by a factor of 100, you can only barely see some kind of peak here. And with this, you can go all the way down to just one or two molecules and take the wrong spec, or you can have resolution of about 10 nanometers. It's a contact technique, but you can go all the way to super resolution with this. So if anything is kind of different from the other images, then you can put this one and make this image.
Quick question on that. Does the tip have to be metallic? Is that a conductive tip?
It can be also semiconductor. But if it's metallic, it's much better. It's like the lightning rod effect. So you're going to enhance it quite a lot. But then for example, optical tweezer, my optical tweezer, the homemade one, gave me force of 200 piconewtons. And sometimes to break protein bond, you need something like 600 piconewtons. If I do not have this force with the optical tweezer, I can use this. That's an AFM image as well. Okay, so you have an AFM on top of your optical microscope, like here, and you can have optical measurements or AFM measurements at the same time.
I have a question. Would it be possible to use nanoparticles for similar kind of enhancement and perhaps also manipulate them with tweezers to bring to the individual cells?
I heard people using carbon nanotubes to do that. It's clearly possible for you to put a quantum dot on top of any of these tweezers and bring it close.
Metal plasmonic particles.
Excuse me?
Plasmonic metal particles.
Metal particles. But I think it's going to be kind of tough for you to manipulate, no?
Possibly.
Yes. If you do have a product that you can sell, I would buy it. I promised the biologists that I would buy all the commercial systems. So this is the one that they have. This is a company called JPK from Berlin in Germany. So they have another one in Israel. They claim that their tip is not like this, it's like this. So you can even see the transmitted light. So you don't lose the transmitted light. So let's see a little bit of the example, otherwise it's going to be too much talk. Anything showing here. So here I have the TAG image of potatoes. Here we have second generation, this is the green one, and the fluorescence of hematoxylin in the using of a half fibroma. Here we have ovarian or adenoma with second harmonic. That's our optical tweezer working here. That's they call trypanosoma crus. It's close to the wall of the intestine of the insect, and you see it can try to bond to the wall there. This guy here is quite unhappy. It's trapped in the optical tweezer. It's trying to escape. And we have red blood cells there. I have one optical tweezer here, another optical tweezer there. You can see we can make a color out of red blood cells. Let me show a little bit of image. This why it's not passing. That's a time-lapse measurement. You can see even cells dividing here. That for that you need a self-controlled focus, self-focusing system here, automatic focus in order for you to let that for 1 day or so and get the image of the same planes there. This just came out from my collaborators. I don't know exactly what it has in terms of biology, but it's kind of pretty, so I decided to show you. I know that they are neural stem cells, they call neurospheres, and they mark it with DAPI, the nucleus, and the red is photoid of the actin fibers. The main advantage of multiphoton microscopy is the fact that if you go to the infrared, your scattering is it's 16 times less scattered than with the visible one. So with that, that's not my measurement, that is the one that broke the record. The movie is not playing, but you can see here that it can reconstruct an image all the way to almost 900 microns, which is about 1 millimeter. In terms of optics, this is amazing that you can go down to 1 millimeter here and take the image in this depth here. Now you can use second harmonic generation. There are main generator of second harmonic signal in biological tissue are the collagen fibers. And if you go to plant cells, it's starch here. And for you to have second harmonic generation, you need non-centrosymmetric molecules. But you can use this because, first of all, electric fields can break the symmetry, and interface can break the symmetry. For example, this molecule is completely symmetric, but as soon as there's oxygen bonds to the surface, it changes and breaks the symmetry. So the second harmonic generation will show pretty much the interface, and while the fluorescence will show everything there. And if you have electric impulse into the nervous systems, each time that one impulse comes, you're going to generate second harmonic generation by that time. So people have used fluorescence to do that. The only difference with fluorescence is that they have photobleaching. And so you can do this for 5 or 10 minutes, but not later. And with second harmonic, you can do this as long as you want. Here are the image of the aorta, taken from this position to that position there. And you can see with red, the second harmonic, those are collagen fibers. And the elastin fibers you can see with fluorescence, so you can see the green ones. And we can show this with people that have normal blood pressure, people that have hypertensive people, and we can actually use algorithm here like construct entropy for each part of this and see the organization of those fibers, count the fibers, and so on and so on. So then the pathologist came to me and asked, I want to make sure that we are looking at the collagen fibers. So let's use the normal picroseries stain that they use to see collagen. Okay, so that's a fixed sample. And then you put SAG together with the fluorescence, and you see that you only see one color, which indicates that you are just seeing the same thing. Then even though that you can say, I can see collagen by just using picroseries stain, there is a big difference here. First of all, our sample is not stated, which means that you can go to in vivo or ex vivo experiments. They are the one you kill your sample. So it's not good to see any biological process. Second harmonic generation does not show any photobleaching. We can go deeper penetration, and we also have more information because depending on the size of fibrils, the amount of light second harmonic generated in the forward direction and backward directions is different. For a very small thickness of your sample, the light is about the same. As soon as you get bigger and bigger, the amount of light that goes to the forward direction is much larger than the one that goes to the backward direction. And this is kind of general for any non-linear optical signal here that you can have. So by measuring the backward and forward one, we can actually extract the thickness of your fibrils over there. And of course, you can use polarization as well to see the best signal. Although you will have to be very careful if you want to use polarization with biological samples, because it scatters the lights all over the place, so you never know the polarization at some position of your samples. That aorta, we can do moves like this. We are showing here fluorescence, and the forward and the backward second harmonic generation, and then the computer will reconstruct it and play around and make nice animations. And we can take that kind of measurement with this called gliding box here to measure, take the Fourier transform to take the entropy of this and try to make it sense with the things that you know. Third harmonic generation is kind of interesting because even though you can have a very high Chi3 sample, it would not generate any third harmonic generation in a homogeneous sample because there is a phase shift above and below the focus that will cancel out the signals here. So it's very sensitive to interface. Okay, and in biology, one of the great generators of third harmonic are the lipid membranes and lipid droplets. But as soon as you have an air droplet, you're going to see third harmonic generation as well. Third harmonic generation is kind of hard because if you want to use twice of our laser, the most you can go is 1040 or 1064 if you use a chameleon. And if you divide this by 3, you you're going to be at 340. I did not see any tetraharmonic in my new Zeiss microscope, and I was thinking, where is it's being lost there? And then I discovered that the mirrors that they use, although they are metallic mirrors, they have a coating that would kill everything below 350. Okay, so, and with the Olympus, I had a kind of a movable PMT that I just put in front of my sample. I did not use the condenser, I did not use anything, I just put it in front of it, and the third one was there. And the Zeiss system, I don't have this movable PMT, so I cannot use it. If I try to unplug, and then the security of the system will turn off the whole system. So I'm still fighting to, I think I have to send the third one generation through some other pathway to reach the detector and try to change Zeiss system in order for it to detect and to reconstruct the image. So that's the potato. Potato is nice. If you want to see if your system is able to detect anything, take just a piece of potato at your first shot that you have, and that will generate second harmonic, third harmonic, and autofluorescence. And buy the cheapest potato you can. Do not buy organic potato. They have less autofluorescence. Buy the one with lots of chemical in it, and then you can have everything. And the nice thing about third harmonic generation is that it can show the nucleus. And for pathology, that's a very important information. The nucleus and their localization here. So that's breast, that's normal breast tissue here, and you can see with red the second harmonic, the collagen fibers, and this is the word in English, can you say milk duct? Milk duct? Is that the scientific word for it?
Or mammary gland?
Yeah.
No.
But you can understand. And that's the way, that's the position that the usual breast cancer starts to grow here. And so if you want to see a nice interface here, covered with two layers of cells, two nucleus, then you know that everything is okay. And this was our first attempt to collaborate with people that work with stem cells in the University of São Paulo. And here we show, we're going to start to study a lot of zebrafish because we can see it since the beginning. So we can see all kinds of transformation with the cells and measure with all the tools we have. You could see the eyes of the zebrafish here. We are looking with second harmonic and autofluorescence. I did not find any sample yet, biological sample, that by just tuning the Thai-sapphire laser, we could not find at least one autofluorescence. We always can find some autofluorescence in these normal biological cells. My friend wants to mix up the system to build collagen fibers, and they have this enzyme that they call MMP that is responsible to cut the collagen fibers. And he used for the prostate cancer, for the prostate tissue here, that's the normal one. The normal one to grow, you don't want it to have too much collagen fibers that is going to squeeze you. So this MMP is going to work, and if you mix it up with this small interference MMP2, then it's not be able to cut all the collagen fibers, so you end up with a lot of collagen. That's going to be kind of important if you want to do any kind of tissue engineering, because the scaffold is very important for the way that the tissue will grow. The other day he took the whole prostate of this newborn mouse here, and we are looking at 2 second harmonic and 1 fluorescence here of all the depths of the prostate of the specimen. But the best thing we want to understand is related to cancer. So people that start this second harmonic generation, they already discovered that you can have the signature of the collagen arrangements here. This is kind of normal, but that's not malignant, but it's not normal, because you see the dense part of collagen. Here you have a tumor, but the collagen, they are organized tangential to the tumor tissue. If you do start to have collagen fibers perpendicular to the tumor, that almost means metastasis. because the cells can use the collagen fiber to move around, like a highway here. And this guy from England, he did show this move in his Nature paper, showing that the cancer cells, they use the collagen fibers to move around. So each time that you do have this kind of arrangement of your collagen, it's very bad for the person that has this kind of cancer. It probably means that some cells have escaped and migrate to other organs of your organism. And those are a sample from the people for the Women's Institute in Unicamp. That's a normal tissue. Here you see all the collagen there just around the tumor. And this case was the one that evolved to opt. The patient was dead. After some time, you could see the collagen fibers organized in that way. And now, let's try to use everything we can. Those are samples that are stained with hematoxylin and eosin. That's the standard procedure for clinical pathology. And the point is that people can get this kind of sample and store it for 15 years or more. So you have a whole library of these samples. So if you can look back at those samples with these new techniques, we can follow up in time what happened in the past already. So that's the one reason to use third hormone generation with this. Here we see third hormone and second hormone. You can see the fibers organized this way. For the cancer one, you can see the fibers going kind of perpendicular to the interface. And you can automatically, by computer, count the number of nucleus. And for the normal one, you have a much lower number than for the tumor one. The number of nucleus on this side of the interface here. And because you can see only the second harmonic, then you can take the Fourier transform of this, and if you would have everything parallel like this, your k vector is going to be in this direction, and actually you can do with the computer, take this kind of ellipse here, and automatically, in position by position, try to find out the directionality of these fibers without the need of anyone to look at it to see. Although here it's kind of easy to see the organization of them. And automatically you can count with the third harmonic the number of nucleus. Let me show you the usual image that a pathologist should look like to give a diagnosis, and that's the way that they give the diagnosis for cancer today. So they like this, they are in the brown phase. So everything is colored with HE, and they look at different colors to punch out what is nucleus, what are fibers, what is not. So that was the image taken with the camera right in front of your ocular of the microscope. And now, that's fluorescence, that's second harmonic, that's third harmonic. So you can take all these images in different detectors, so they are separate, and you can mix them. Fluorescence with second harmonic, fluorescence with third harmonic, second and third harmonic, and then we can put everything together so we can look in terms of colors at least. We have a much nicer image than the normal one that they shall look. The important point thing here, I believe, is the fact that we can have different images with a very high contrast. So I can see only the collagen fiber, I can see only the nucleus, and the pathologists, they must recognize which is which, because they see everything together. Yeah. And then we can separate. And then it's going to be much easier for the computer to count it automatically than with the eyes of pathologists. Cornea, completely collagen-made tissue. It must be transparent. There are some diseases, and we are studying this kind of disease with some treatment here to see if we can change the collagen structure. This is a disease called osteogenesis imperfecta that appears in the collagen buildup of the body here. That's the normal skin tissue of a normal person, and that's for the one that has this kind of condition. If you use bones, we have seen autofluorescent and second homogenization out of just a piece of bone. And for burned skin, we can see the reconstruction, how it heals and how it builds up back again the collagen structure here. We have two autofluorescence and the second homogenization out of this. Let me show you the FLIM, because I like the FLIM and I want to use it. That was the first FLIM image made in Brazil. We had done with the same aorta I did show you, and this was done with fluorescence and second harmonic. You can see the collagen fibers between the elastin fibers here, and the FLIM is very sensitive, for example, for NADH and FAD that are pretty much related to the cell metabolism. So it's a good indicator of cancer and metastasis as well. So the point is that if you just use a fixed sample, the chemistry around your molecule, it depends much more on the treatment that you made into your sample than on some biological principle that you have there. So I want to have this first with some living stuff, so I just use leaf of oregano, and you see here the color. The color is depends on the time of your FLIM, and that depends on the amount of oxygen or pH or any iron concentration. And you can see that in the stomach of the plant, that's the position where they breathe. They breathe from this part here, and you see this green stuff. They are the chloroplasts there. And you can see the change in color of this part quite a lot here. And we also have this graph here that you can see the number, how much you have in this lifetime, and how much you have in this lifetime. You have the decay curve here. You can make a fitting with 1 or 2 or 3 exponential here, and then you can play around and make images of the ratio of the two or anything that you want. So that's the theme of oregano. You can see 2 peaks here in the lifetime of the fluorescence, and I wanted to use this with some living stuff. So we get this Langerhans island that are inside the pancreas to process sugar. And then what we did is just we have the control one here. That was made at room temperature. They usually should be done at 37, 38 degrees Celsius here. But you see that you have this bright spot here, and then we add a solution of sugar, and then you see it starts to, let's look at the histogram here. You see the 2 lifetimes here, and it's changing, and after 10 minutes of glucose, you can see lots of change in this one here. Anytime that ion channel opens, you're going to see this change into the lifetime. In Brazil now, we are making ethanol out of sugarcane, and one thing that people just hate is lignin, because you cannot destroy lignin, and it always makes it hard for you to extract more sugar out of the sugarcane. So the point is that lignin is kind of a phenol, and they have different kinds of lignin. And my friend wants to know where they are. And if you try to, it's fluorescent, so it's nice. It's fluorescent in green. But the point is that you cannot distinguish them just by the fluorescence wavelength. But with FLIM, if you see different colors, spatial localized, it means that you have information here. And so with FLIM, we can decide where they are, we can use it in plants, and even for fixed sample, that's just the second harmonic for the normal ovarian tissue here, and you see both of them here, and even though it was fixed and processed, just take the FLIM image. You can almost see everything that you have here and there in just one picture. Because second harmonic is going to be very fast. Second and third, but you have fluorescence here. So you could almost see the 2 peaks here and separate them. Cars. The main reason that people do not use Raman to make an image is because the Raman is so weak that you should, if you have to integrate for 10 milliseconds for each pixel, and you want to make a 1 megapixel image, it will take 10 to 4 seconds. So 3 hours to make an image. So people usually compromise the resolution to make less amount of pixels to make it faster. If you want to observe any cell process that can last 10 minutes, you are dead. You cannot use it. Although it's very nice for you to stop at one spot here and take a spectrum, that would last a minute or two to take just the spectrum to know what you have there. To make an image is kind of very, very slow. If you can enhance this by a factor of 10 to 4, like cars, because then everything is coherent and you can drive the nucleus by the beating of the two lasers. They are exactly the difference in frequency. It's exactly the nucleus vibration. So now the nucleus will vibrate coherently with the laser, and if you enhance it by a factor of 10 to 4, you can take the same image in 1 second instead of 3 hours. That makes a lot of difference. And you can tune the lasers to any Raman line you want. Okay, so at least you expect that this Raman line is very intense for some region of your sample. So that was the first cars image made in Brazil. The laser came here 3 weeks ago, and we did what everyone does when they just got a new brand cars laser system. You just take the ear of the pig that's full of fat and tune it to 2,900 in that centimeters. That's the lipid Raman line for the lipid, and make the first image, and you have a hair part of the ear of the pig as well. The optical tweezers, we did not get the brand new optical tweezer yet. We only had the old homemade optical tweezers. We have used for lots of stuff. I showed you just a little bit of them. One was to understand chemotaxis of leishmania. Here we just put in a concentration of glucose here, and first thing you can do is to look at the movement. You see that's random movement of the leishmania here, and as soon as it's discovered that there is a sugar concentration, it starts to run around in circles. So it's like it's kind of measuring the amount of sugar here in a larger region in order to decide the direction to move. And we also trap it and measure the force, and we can measure not just the strength of the force, but the direction of the force, so we can see the chemotaxis of this kind of microorganisms by just looking at the tweezers, and you can control the concentration here as well. And this guy here, the idea is to bind itself to the wall of the intestine of the insect, and then it moves, and then it becomes contagious at this point here. We never work with this because I'm pretty much afraid. We only work with this is not contagious, so we can play around with it in our lab. And this kind of trypanosoma, they like to bind at this position here, but they do not bind to the gland of the mouth of the insect. And we did bring it with the optical tweezer close and measure the force here and the directionality of the force. So we bring it close to the gland tissue, to the tissue of this part here, and to the tissue of that part. And we discover chemotaxical behavior right only close to this one. And if you go around about 100 micron here from the wall, it just do not feel anything. Okay, but as soon as it gets close to the wall, it starts to try to bind. And it's the same, because if you look at the tail, it tries to bind the tail at the wall. Okay, so the movement is kind of strange. It's not direct to the direction of the wall, but it's trying to, because it always binds with the tail here and not with the head. And we play a lot with spermatozoid. We did find some small pretty crystal inside onion cells. It's kind of nice, but they discovered that it can become a kidney stone, so I stopped to eat onion, not that much anymore. We could use laser to destroy stuff like this here, just shine a laser with thermal effect here and then send away. It would be nice if you use this to take all this blood clots that you could have in your blood system and clean everything. Actually, people tried to do this back in the 80s, and then they discovered that in 30% of the case they would punch a hole at the wall so they stopped to do that. It was not fun anymore. You can use this to punch strings from the layer, membrane here, of your onion cells. You can make the color of red blood cells. We can trap bacteria and they stay alive there. You can see that when you turn off the laser, they will go quite happy out. Actually, sometimes we trap 1, 2, 3, depends on the power of the laser. And at some point, they required us to make these movies available at the internet. And then I discovered my name into a UFO site. Because they claim that if they can use a laser to trap bacteria, why not OVNI spaceship could not shine some light on some person and just suck it up there. So, and the title was Light Sights. So I was complaining with my friend that required me to show on this book, and he said, don't worry, as long as you make the information available, they can use for whatever purpose they want to do. I did not tell them that they could actually do this if they had enough power, but the only thing that they would get there would be people's power. Not state, not even state. More than a well done, nothing left. But actually the article was not saying that they actually sucked the whole person. What they did was they sent the first laser, like this one, to punch 3 holes here at the neck, and then the autofluorescent just to suck the blood. So the guy was still alive after that. It was great. So they want to have our blood. And you can also have autofluorescent with confocal microscope. So, and here we have our homemade system, and now we're going to have, actually we have to ask for a special order for them to fit into our size system, and they have to fit right on top of the non-discount detectors that we have there, okay? And use the right dichroite to send it there. But I believe in August we're going to have the system, everything put together. So we're going to have Raman, cars, multiphoton microscope, second and third generation, with the size not tetramonic yet. Any fluorescence detector with forward and reflected light. And the autofluorescence plus the tip enhancement on top of it. Everything into the same microscope. Okay. So I hope that you guys start to ask for the companies, do not make that mirror that would kill the 350 anymore, because then we don't have to buy a new laser just to get the tetramonic generation. People are buying lasers at 1200 nanometers to have the tetramonic at 400. So with the price of fire, you could have the tetramonic generation quite easy if the optics will not would allow you to do this. And it's very easy for the company to do, but it's very hard for you to change after you buy. It's kind of difficult. I believe I will stop here. I would love to do lots of Fourier transform calculations, because I saw everyone doing Fourier transform calculations here, but I think my message is much more experimental than theoretical for you. Okay, so I thank you.
Well, that was a tremendous array of really beautiful animations. Put the rest of this to shame in terms of graphics.
I have a friend that used to say that if you know something, you present it in black and white. If you don't know, use colors. If you know nothing, then use animation. That's
Well, let me
but
ask.
the point is that he's buying a new Zeiss microscope as well. So
Let me ask you a general question. I mean, you show lots of beautiful images of very fine microstructures. To what extent do you have to stabilize the living organisms so they're not moving around? And how do you do that?
That's a kind of problem. If you do have the autofluorescent, then you're going to try to trap them, but they can kind of move around like the microorganisms that we have seen. Okay. The way that the biologists may do to get rid of this is to actually make them to glue on the bottom part of your cover slip. So they have some kind of coatings that the samples go down there and stop there. For example, we do put quantum dots into this kind of microorganism, and we have been able to see the fluorescence spectrum very fast. As soon as we see the image, we can take the spectrum. Okay, even though the image is quite fast. Yeah. So for us to understand at least what kind of quantum dot he ate, if it's there, and stuff like that, we can do. But, for example, if you want to make a Raman spectrum of some living organism, and you do not stop it, it's going to be hard. It's going to be hard. Although, with the system that I showed you, wherever place you are scanning here, you're going to be at the same spot size at the entrance of your monochrome. So, you could do this scanning, but then you're going to have lots of all this stuff, and you're going to take the spectrum of everything. So if you know pretty much and have a contrast for the run of just what you want to see, it's going to be great. If it's a crawling movement of cells into the bottom part of your cover slip, then it's slow enough that you do not have much problems. We also bought a system that they call spinning disk. Spinning disk is very fast. It can take images in the frame rate of 100 frames per second. Okay, so, but only fluorescence and white field. It's not focalized, focal laser, scanning laser. Okay, so with spinning disk, we're going to be able to see some of this, but we did not have the same situation we have here. Although Sunny Shi, the pioneer of cars, he did show video rate images of cars image. Cars can be quite fast if your detectors are very sensitive, so you could use them. But at this point, we work it with kind of slow processes, and we are gonna see what I pretty much decide to do is to look at the cells, at the embryos developing, so I can see all the transformation that the stem cells can do to differentiate, and why it cannot come back. And this is kind of a slow process. It's kind of a slow, so we can follow it. If you do not use autofocus, you're going to start to have problem because the focus drift through the time. Temperature changes a lot during the night and the day, so, but it's already built there. It should be working fine. It did work fine for at least 4 hours with this.
Any additional questions? Now, let's thank our speaker one more time and all the speakers today. And we resume tomorrow.
We have